Good morning. Please take your seats. Good morning, everyone. My name is Karlheinz Bock. On behalf of the ECTC Executive Committee, I'm serving as the General Chair of ECTC this year. A warm welcome to the opening of the 74th ECTC, the flagship conference of the IEEE Electronic Packaging Society. Today marks the culmination of months of hard work and collaboration. We gather here today to express our sincere gratitude to all those who have made this event possible. First and foremost, I would like to extend a heartfelt thank you to our sponsors, whose generous support has been instrumental in bringing this conference to fruition. Your commitment to our shared vision and your investment in our community has allowed us to create an enriching experience for all of us. A special appreciation goes to our exhibitors, who showcase cutting-edge technologies just around the corner. Please go there to see innovative products, groundbreaking solutions. Your presence, dear exhibitors, adds tremendous value to this conference, creating opportunities for engagement, networking, and collaboration. I want to express my deepest gratitude to our esteemed speakers and panelists who have traveled far and wide to share their expertise and insights. Your wealth of knowledge, research, and experience will undoubtedly inspire and enlighten us all, setting the stage for meaningful discussions and profound learning. To the technical program committees, volunteering here, more than 230, your tireless efforts in reviewing papers, organizing sessions, and ensuring the highest quality of content have been instrumental in curating an outstanding program for our attendees today and in the next days. And of course, a warm thank you to each and every attendee. Thank you for being here. Thank you for supporting ECTC. We are really grateful to you to keep our community alive. So your enthusiasm, engagement, and diverse perspective will shape the conversations and interactions that take place over the next few days. You are actually the lifeblood of this conference. Thank you so much for being here. Last but not least, a cordial thank you to Lisa Renzi and her conference organization and management team. They were shaping this conference for your best experience and convenience in so many aspects. So please, enjoy the remarkable conference program now ahead. Some logistical items I would like to mention. Everyone please sure to install and use the VOVA app, ECTC VOVA app. The entire program will be up to date. Information is in this app, and it has a very nice messaging platform for networking. Also, we are conducting paper scoring for a number of awards through the app. So finally, this is also important, after the keynote, we will have the Q&A with our keynote speaker, and we are collecting questions through the app, so please give it a try. Now, without further ado, it is my great honor to introduce our keynote speaker, Professor Keren Bergman, to you. Keren Bergman is the Charles Batchelor Professor of Electrical Engineering at Columbia University, where she also serves as the Faculty Director of the Columbia Nano Initiative. Keren Bergman received the Bachelor of Science from Bucknell University in 1988 and the Master of Science in 1991, and her PhD in 1994 from MIT, all in electrical engineering. At Columbia, she leads the Lightwave Research Laboratory, encompassing multiple cross-disciplinary programs at the intersection of computing and photonics. Since 2023, Keren Bergman is the director of the Center for Ubiquitous Connectivity, CUBIC, a 5-year multi-university centered funded project by DARPA and the Semiconductor Research Corporation, SRC, under the Joint University Microelectronics Program 2.0, JUMP 2.0. Keren Bergman serves on the Leadership Council of the American Institute of Manufacturing, AIM Photonics, leading projects that support the Institute's silicon photonics manufacturing capabilities and datacom applications. She is the recipient of the IEEE Photonics Engineering Award and is a fellow of Optica and IEEE. Keren Bergman's insights and expertise will undoubtedly set the tone for an exceptional conference filled with inspiration and discovery. So, ladies and gentlemen, please join me in warmly welcome our keynote speaker, Professor Keren Bergman. Please. Thank you.
Thank you so much. Good morning, everyone. And just a really warm thank you to Karlheinz and the committee of ECTC. It's a real honor to be here today. I will talk about photonics and the application of the emerging field of silicon photonics, specifically to large-scale computing systems and the new generation of AI computing. As many of you are, I'm sure, aware, AI applications are dominating the computing world in data centers today. The growth in these applications is unprecedented. 6 orders of magnitude in just the last 6 years. Have you ever seen anything that grows by an order of magnitude per year? It's beyond our imagination for technology to grow so quickly, and it does not seem to be abating or slowing down in any way. Today's systems can have parameters, application sizes, model sizes that are over 10 trillion parameters, and clearly exceed the memory capacity that's possible within a single compute socket. So how do we scale these very quickly growing computation applications? At the same time, it's very important to also note that there is a tremendous growth in the energy consumption associated with these applications. As you run these huge training models, for example, the amount of time that it takes to complete the training on a very, very large data center actually consumes a tremendous amount of power, energy. And you can see here, and I just want to point out that this is on a log scale. You can see here the energy consumption in megawatt hours versus the parameters that are being used in these large models as an example. You see GPT-4, all the way up there at the top right corner. So just to put this in a little bit of a frame of reference, I drew a line. This is the average power delivered to the entire city of New York in 1 hour, 5,500 megawatts. During the summer, when it gets very hot in New York City, it can jump. We've had power outages. That's approximately 32,000 megawatts delivered in an hour. So just to put that in perspective, we're facing a significant energy. Energy is not something that scales very well, as we all know. And this has hit the front page news, as I imagine many of you have already seen. The global energy consumption of AI is beginning to really have an impact. Data centers operating around the world are actually impacting the power grid, energy grid. So how do we address this? Because we're not going to slow down these AI systems. They're just, as I showed you, they're just growing so incredibly fast. We need to figure out a way, and I will talk about photonics as really a mechanism for continuing to enable the performance scaling of AI, but at the same time, bending the energy curve. So the goal here is to continue to scale performance, maybe by another 1 or 2 orders of magnitude, and hopefully more. But we need to flatten, or at least bend, the energy consumption curve so it doesn't continue to grow exponentially as it has, because we all know that the energy consumption does not scale. We cannot start to have nuclear power plants next to our data centers. So the first part that I would like to discuss is what exists today in terms of connectivity solutions, and how do we bring photonics into these systems? And of course, a big part of that is a packaging problem, which of course this conference is focused on. So what you see here on this slide, on your left-hand side, is a curve that was actually developed by a DARPA program manager, Dr. Gordon Keeler, a few years ago, that initiated a DARPA program called PIPES, which we had the privilege, are part of. What this curve shows is on a y-axis, or the vertical axis, is a metric, a combined metric of bandwidth density and energy consumption. So the higher we are vertically, the better this metric is. The lower the energy consumption and the higher the bandwidth density. And on the x-axis, the horizontal axis, we see the reach of the interconnect. How long can the signal propagate? So for very, very short distances, meaning within the chip, on the chip, electronics is actually very, very good. And the folks here, of course, know that very well. Typically, within the chip, over 3D integration, very short distances, we can look at femtojoules per bit and very, very high bandwidth densities. So you see those green squares and red circles. They represent these state-of-the-art electronics. However, as soon as we move the data over any appreciable distance, across the board, maybe to external memory in the system, that figure of merit really starts to drop very, very quickly. Because the energy consumption of moving the data goes up with distance. We have losses, we have lots of losses in the electronic waveguide. And thereby, the energy density, the bandwidth density, of course, is reduced. And what you see at the far end, the lower right-hand side, are some of the current state-of-the-art photonics. So those are you can go and they're commercially available, what we call the pluggable photonic technology that we see in data centers today. And the reason we're using photonics there is because they can carry the signal over long distances, over fibers, but they're not designed for energy efficiency. They just use conventional semiconductor lasers and some optical modulators. They're just not designed to be very energy efficient because that wasn't the goal there. And they're definitely not designed for bandwidth density. Typically, those pluggables today are about 400 gigabit per second, maybe 800 gigabit in the very next generation. Not terabits per millimeter type densities that I will show you that we'll need. So what we want to do, the goal here is to think about embedding photonics. There's a new generation of photonics, integrated photonics in silicon. And how do we bring that into the package in a closely integrated fashion to actually get those two very important metrics simultaneously? I want to emphasize that just getting an energy efficient link is not enough. We need both energy efficiency and bandwidth density together. And that's really the challenge. So you can see the picture, the vision for this potentially heterogeneously integrated future package that has a photonic, if you will, chiplet, I/O chiplet. It's part of this ecosystem, and it can connect to memory, can connect to the processors, GPU, et cetera, et cetera. So let's go back and look at the systems today on the other side, the compute socket. And what are the numbers that we need to actually achieve, right? If we look inside the socket, the bandwidth densities, the bandwidth that's in there is tremendous. For example, you can see some of this key industry commercial packages that can have terabytes, multiple terabytes of data communication. This is within that package, typically from the GPU to memory and so forth. So these are very, very high bandwidth densities, and as I showed you, the metric there is very good, femtojoules per bit energy consumption. Within the board, it's a little bit less, because now we're going over slightly longer distances. We might be going through something like an NV switch, or an infinity fabric, and so on. And so the bandwidths drop down a little bit, maybe by another factor of 10, but it's still quite high. But dramatically, as soon as we take that data outside of the socket, across the system, and this is about communicating over maybe multiple meters to maybe up to a couple of kilometers across the entire data center, the bandwidth, this is when we start to use those pluggable photonics, like InfiniBand, that are 400, maybe 800 gigabits per line. And so we can have as much as 2 orders of magnitude, maybe even more, of available bandwidth density as we start to go over those longer distances. And the energy consumption is not very good either, because again, those pluggables are just not designed for that application. So in this new world of AI systems, we really need to rethink how photonics can be used really within the compute system itself. So we have a world of silicon photonics. This is a technology that has really emerged in the last almost couple of decades now. And today we have multiple fabrication capabilities around the world, Asia, Europe, in the US, and many of the top companies in the world are now emerging themselves into silicon photonics. And running 300 millimeter fabs, routinely, and many companies are looking into fabricating silicon photonics. You can see some of the devices. We can basically now make all the key components of a link, including the data modulation, data multiplexing, filtering, and data reception. With the exception of the laser, and I'll talk about the laser. This is one of the key differences between working in the optical domain versus working in the electronic domain. Electronic, you can just have a voltage source. It's just right there in your circuit. With optics, you have to think about where the laser is coming from. And I just want to make it very clear, we don't have a laser in silicon. Silicon is not a direct bandgap, and so it just does not work to make a laser in silicon. And so we typically have lasers that are in 3-5 semiconductors, and we have to somehow think about how does the laser fit into our package. There are many different techniques for that. Okay, so I want to talk a little bit about how photonics is, at least today, being thought of. How is it integrated into the package, into the chip? We have 2.5D integration approaches. You can kind of see an example of that here, where we have an interposer and an electronic chip that's used to be the interface to the optical chip, the photonic chip, the PIC, if you will. And then the interconnect is going through an interposer. And you can see a picture of that implementation. So this is a pretty good technology because it's very flexible. We can think about putting other chips in this 2.5D package. It allows for some amount of thermal isolation and so forth. But you can see below that it really doesn't achieve the bandwidth densities that we want, because we have to put the electronics in some place adjacent to the photonics. And so the area that we have and the kind of density that we can achieve is really on the order of a few hundred gigabits per millimeter, which is actually similar to what electronics can achieve today. So we're not really extracting the bandwidth densities that we want to have out of photonics with this geometry. And the energy consumption is okay, but not very good. It's a few picojoules per bit. We can think about monolithic integration. This is a really interesting technology. So this is a technology that is, you have a foundry with a process, and you can actually design and fabricate electronics, electronic devices, electronic transistors, as well as photonic devices, all in the same process. So you get out one wafer, you get out a die, and it already has monolithically integrated electronic drivers, electronic receivers, as well as the photonic devices. So this is, from a packaging perspective, this is almost an ideal approach. And this is a kind of a picture of one of the technologies, commercial technologies available that does that. And it has minimal parasitics, it simplifies, really importantly, really simplifies the packaging. However, the bandwidth densities that you can achieve, again, are limited. Why? Because we live in this two-dimensional world with the monolithic integration, right? You think about the photonic devices that you have to place there, and then we need to put the electronic transmitter, driver circuitry, typically in RF speeds, 10, 20, sometimes 50 gigahertz, driving those photonic devices. We have to have the receiver electronics next to it. And you want to keep those distances very short to minimize parasitics. And so it limits your layout, limits how much you can put on that surface. And so the kind of bandwidth densities that we end up getting from these type of approaches are, again, on the order of a few hundred gigabits per millimeter. And that's it. We're limited to that. There's not really capable of scaling beyond that, because we have to lay out the electronics near that. So that's a limitation. Another limitation is that, unfortunately, there's very few foundries in the world that offer this kind of process. One, of course, very good one, of course, is Global Foundries. It's a great process, but it doesn't let you separately optimize the electronics and the photonics, right? You're stuck with the process that you're given. So you can't, for example, use the most advanced electronics process and then combine it with the photonics. But again, I want to go back and say one of the biggest challenges for photonics is the package. And so the monolithic approach is, its big plus is that it solves the packaging problem very, very well. Okay, and then the third approach that I'd like to talk about, which is the work that my lab is mostly focused on, is the 3D integration. So this is an approach where we basically fabricate the photonics in a photonic optimized process, which, as I mentioned, there are multiple foundries in the world that will do that. And then we can fabricate the electronics in another process. And basically, we can then either combine the photonic, at the wafer scale or at the die level, different approaches in a 3D integration to combine the electronics and the photonics. And this approach gives us the best possible density, bandwidth density, because we can pack the photonics as dense as we can on the photonic chip, and we can pack the electronics to match that. And then we can, with the 3D integration, obviously we minimize the parasitics tremendously, right? Because that's the shortest distance between the two. But, the downside, of course, is that it's a complex packaging process. It's a 3D packaging process, needs to be developed. And another important issue is the thermal. If you have an electronics chip that's running very hot that can affect the photonic chip and so forth. So we have to look at the thermal characteristics very, very closely. On the metrics, we want to get the performance. This is really the best approach from that point of view, right? We can actually get multiple terabits per millimeter edge bandwidth density and approach sub-picojoule per bit for the communication distance. And hopefully I convinced you from looking at the requirements from the compute socket. As you recall, we saw terabytes of communication bandwidth and very, 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 very low energy consumption. So I will make the case here that this approach, the 3D approach, is really the only way to successfully insert photonics that actually meets the performance requirements that's needed from the compute socket perspective. So this is the approach that we need to go to for AI systems. Okay, so how do we get there? There are some really great advantages to optics, and also some great disadvantages to optics. One of the great disadvantages to optics is that it's very difficult to do processing, processing in the optical domain. We don't have an equivalent nonlinear element like the transistor to do that. There is, of course, a lot of research in the domain of optical computing, but in general, I will make the case that it's really not anything that's on the horizon at the moment. But what's really good about photonics is that we can communicate with extreme bandwidth densities because we can combine multiple signals in the same waveguide by putting those signals on different wavelengths, right? They're not going to interfere with each other. If we combine multiple electrical signals in the same wire, obviously that's not going to work due to interference and crosstalk. In the optical domain, we can do that very easily. So the approach is to put data on multiple wavelength channels and then combine all those wavelength channels into one pin, one interconnect. And that gets us, and then of course have multiple of those photonic wires. And that gets us to achieve very, very high bandwidth densities. In silicon photonics, the way that we achieve modulation on different wavelengths is using devices that you see here. They look like these disks. They're disk modulators. And what they do is they basically do two functions at the same time. They select a wavelength, and then you can drive them electronically to modulate the data onto that optical channel. So in this picture, what we have is we have a laser source, and I will talk a little bit more about the laser source. The laser source comes into this chip. The laser source actually contains multiple optical wavelengths, all at the same time. So imagine it's a comb, we call it a comb laser source. So it's a comb of different wavelengths that are coming into this chip. And the separate disks that you see on the transmitter side immediately select the specific wavelength that's coming from the comb that's tuned to them, puts data onto that wavelength, and then it can couple out, propagate through a fiber, as you see in the picture. On the receiver side, the opposite happens. Instead of modulating the data, we have similarly looking disks, but they are filters. They basically filter out that particular wavelength channel, and then we go into an optical detector and the back end of the receiver. That's the architecture. Because we are using multiple channels, right, we have a very interesting design space here. Let's say I want to have a terabit link, right? A single link that runs a terabit. I can do it multiple ways. I can go to one extreme and have one optical channel modulated at a terahertz. Obviously, that's not a good solution. It's very hard to do. It also will consume a lot of energy, right? The higher the frequency, the higher the energy. I can have 10 channels at 100 gigabit per second per channel. Okay, that's possible. But 100 gigabit per second per channel leads to pretty high energy per bit. It's going to be multiple picojoules per bit if I have to operate at 100 gigabit per second. But I can just add more channels. Let's say I have 64 channels of wavelengths. Now I can go down to 16 gigabits per second per channel. And that design space enables me to now reduce the energy per bit while keeping the same overall bandwidth, right? This is the magic, or the really important design space of photonics. Once I have that bandwidth and energy consumption achieved, a very important point here is that the optical wire, or the fiber, is extremely low loss, right? Fibers have a loss of about 0.2 dBs per kilometer. So once I've generated that data, I can move over very long distances. It's distance independent. Unlike in electronics, as soon as I get out of the chip, as soon as I go across the board, I experience a tremendous amount of loss on my signal. So that's the basic concept. Okay, I'm going to talk about a really important key enabling technology, which is this comb laser source. And I want to mention that together with, you can see there are two names here, Professor Alex Gaeta and Professor Michal Lipson, my colleagues at Columbia, we also have a company called Escape Photonics that's commercializing this technology, as well as the link technology that I will show today. So this is a unique laser technology that we've been developing where we can generate any number of optical channels across a very wide spectrum. You can see here 70 channels of optics. And the comb generates those wavelengths very, very precisely. In fact, in other applications, it can be used for metrology and clocking and things like that. So it's extremely precise. You can see a little picture of the package of that laser. So it's basically a chip. It's sitting on a chip, the same similar silicon chip where we have the rest of the link. But we typically think of the laser as being outside of the main package, primarily because we want to separately we don't want the thermal effects of the laser to affect the rest of the chip. And that's actually a good thing. We can, that we don't want to have it necessarily co-integrated on the same wafer as the links. So we start with this very important comb laser technology. And then this is a lot of details on the photonic design, but I just want to kind of give you the flavor of when you design the photonics in these different processes, these different foundries that are out there, there is pretty extensive design that goes into the photonics. And what we've been doing is really optimizing, co-optimizing the design of the photonic side with the electrical side for the purpose of minimizing the energy. It's important to note that because it's not something that's been done in the past in optics in general. It's been used primarily for telecom applications, and the energy consumption per bit was not a primary goal necessarily. But here it is. And so this is a little bit detailed for maybe the folks that are more optics inclined here. We use what's known as a vertical junction doped modulator. It's a disk modulator. And the reason we go through all that work is to be able to get a very high-speed modulator that only requires a 0.8 volt swing voltage. That's compatible with advanced CMOS. You might hear photonics and silicon photonics. Sometimes you look under the hood and you see, oh wow, this photonics requires 1.5 volts, 2 volts. But that's not really compatible with advanced nodes. So we need to this is a very important part of the design space. We also have what we refer to as a scalable link architecture. You saw this comb laser can generate maybe hundreds of lines, potentially. We want to be able to have an architecture that can really scale into the future, beyond the terabit per link, maybe 2 terabit, maybe 10 terabit per link. This is all possible with this scalable architecture design that we have, where we can separate the modulators into different banks and different buses. So just a little bit of an example that's, again, important with these. So we have this comb. It generates a lot of wavelengths. We have these disks that are modulating those wavelengths. And then we have another set of disks that are filtering those wavelengths on the back end, on the receiver. So you might ask, hey, you know, how are you getting all these different wavelengths aligned to each other? You know, how do you get the bank of the modulators, the bank of the receivers? You know, how is this all working and staying stable and functional? So one of the other kind of under the hood design elements that I want to point out is that some other designs use what are known as micro ring resonator modulators and filters. And the reason we use disks as opposed to rings, just as a small detail, is that besides the fact that the disks require much less voltage to operate, they're also much more robust. So we can design them at a specific wavelength, and they're very close to staying at that wavelength. And so they're fabrication robust, because they only have one edge. A disk only has one edge. A ring has 2 edges, and it's much harder to control. So all these kind of process versus fabrication variations versus the voltage versus the amount of energy that it requires, all of this co-design is a really important component of this technology that I really want to emphasize. It's not just fabricate photonics, fabricate electronics, and stick it together. And so this is an example of some recent work where we had, again, these multiple buses, 64 channels. And you can see here the gist of this is that we designed these to line up with the comb lines, and they come out very, very close to the design, very highly robust. We've been very fortunate. I'm at a university, at Columbia University, and so typically, university, we work with multi-project wafer runs, MPWs, but we've been very fortunate to get access to full reticle runs. And I like to say that now that my students are used to designing a full reticle, which is a lot of work, but also gives us a tremendous amount of flexibility, they don't want to go back to MPWs. It's like flying first class. Once you do that, it's hard to go back to coach. So we've been very fortunate to do 300 millimeter fab runs. We've done them at multiple places, but our primary place is at AIM Photonics, which is in Albany, New York. It's an institute, a manufacturing institute. And you can see the advantage of doing it is that we can have many, many designs. We can iterate, and we can make a lot of progress. So this was our first wafer. We had a second wafer that we called Oak, and so on. And then we even have a third wafer right now that's currently in the fab, right? So what all of this enables us to do is first of all, collect a lot of data, be able to iterate on the process and the designs, which are really critical to all of this development. And this has been, what I'm showing you is multiple years of development here that's behind us. In addition, we've also been very fortunate to get, so how do you do all the testing, right? How do you do all the characterization now that you have full wafers, with many, many devices? So we have a wafer scale prober, automated prober. I like to say that this replaces about 5 or 6 PhD students, more or less. It can run all night, can collect a lot of data. And so I just want to show that. Importantly here is that it can do both electronic and optical characterization simultaneously. And you can see here we're very concerned about, or really pay a lot of attention to the thermo-optic characterization and so on. And now we can collect statistics, and we can show that our designs are robust or not robust, all the fabrication variations. So it's not anymore about one single device, one single idea, but really about thinking about it from the system level and actually developing these massively integrated components. This is just an interesting addition that we've made, which is, it's called an undercut. And it actually improves the thermal efficiency of these devices. So this is a wafer scale process that we co-developed with the Air Force Lab and the AIM Institute. So now we get to some of the results. And so we have achieved this goal of the 3D integrated electronic photonic chiplet. And you can see here sort of the bonding between the EICs on the top, the PIC is on the bottom. And this particular chip has 80 transmitters, each running at 10 gigabit per second. And you can see all the eye diagrams that we accumulated. And while all of those transmitters are running at 10 gigabit per second each, the total amount of energy per bit is 50 femtojoules. 50 femtojoules. On the receiver side, the energy is just under 70 femtojoules. So about 120 femtojoules for this chip. And this is a picture of the chip. So this is a chip that expends 120 femtojoules for the entire transceiver, and it has a density of 5.3 terabits per millimeter squared. And this is just the beginning. We can run the modulators faster. In this particular work, we actually use just a 28 nanometer EIC, so it's not even that advanced. There's a lot of room to improve on the energy and improve on the bandwidth density. This is the energy consumption of the entire link, where we have to include not just the transceiver, but also the thermal control and the laser. And it's just under a half a picojoule per bit. And I want to emphasize that this half a picojoule is able to carry that data almost any distance within the system. This is almost distance independent. This is a picture, again, of that and a summary of the approach. Another very important part is how do you couple the light in and out of this chip? I know this is a topic that is very hot right now in photonics. So you can see on the left side, the size of the fiber is typically about 10 microns in diameter, single mode fiber. And the size of the waveguide in the silicon chip is typically about a half a micron. So it's a big mismatch. And what we typically use to couple the light into the fiber is we use something we call an inverse taper. It's almost counterintuitive, but we make a tip of the waveguide, and that actually matches the mode into the fiber. You can see how it's fabricated here. But this is a very complex design, and it's also very, very sensitive to misalignment. We also use other techniques to match the mode, such as substrate removal. So again, this goes into some of the packaging challenges associated with connecting the fiber I/O to the chip. This is just a quick video. We have to do epoxy. I want to thank Tyndall Institute in Ireland for this. They're really some of the packaging frontiers. And active, this kind of fiber coupling to the chip requires what we call active alignment. So something that comes to mind as soon as you see this, expensive, 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 right? Right. How do we solve this, right? One really promising approach, and this is again led by Tyndall, we collaborate with, is to use microlenses and actually collimate the light. And I'll just show you a quick, so this is you'll see a little video. So this allows you to have a completely pluggable array of fibers into the chip. And you can see that he can unplug and plug back that fiber array, and the losses, the power remains. So now we have this notion of photonic connectivity, and we want to bring it into the system, right? We want to bring that photonic connectivity perhaps to the memory to enable a system with disaggregated memory and be able to not just have the fibers as they are today with the pluggables connected to the server, but really connected all the way into the socket, right? And that enables us to improve not just the energy consumption associated with the data movement, but improve the energy of the entire system. And what I mean by that is, let me just skip through that because this is a little bit about the 2.5D integration that we use in our system level experiments. You can see a nice picture of the interposer with the EIC and the PIC. I thought I'd put a lot of packaging pictures for you guys today, make it interesting, so as much as possible. But basically, the story with the system level is that we want to think about how we put the photonic connectivity at the system level, system-wide. And the idea here is to not just improve the energy consumption and bandwidth of the interconnect, but improve the energy consumption of the entire system, right, to bend that curve. And the way we do that is by using the photonics to connect only to the resources that are needed for the application at the time. And this is the approach that we're using. You can see something we call flex CPAC, where we have flexible connectivity at the system level. And I'll skip that. And I'll just show you some kind of final results here that what the flexible photonic connectivity can do, now that we have it at the system level, is it accelerates that entire AI application by several factors, right? If I can run my entire application 3 times, 5 times faster, I reduce those megawatts per hour significantly, in addition to reducing the energy of the data movement. So this is where we're going at the system level. So with that, just want to thank the people that actually do all the work. This is our group and our sponsors. And I want to especially thank SRC and the sponsor companies of the Jump 2 Center. So thank you so much.
So thank you so much for this really fantastic, great,
thank you.
Very inspiring talk. So, and I think you will join me in thinking about this topic will be one of the demanding topics in the next years for our community. So thank you so much for building this bridge to our community, coming here from the device level. And I think the packaging community has understood the task now. No? We have to work together for this really challenging approaches mentioned in your great talk. Thank you so much, and may I invite you to go to the chairs, and then we start now the Q&A. So I see already one question has been a long time actually in the VOVA app, and if you agree, I think we may actually choose the one which has the most likes.
Absolutely.
And I would read it to you. So in 2024, year 1 for co-packaged optics, question mark. Could you maybe
comment on that?
Give us your thoughts about that, please.
Yeah, I think this is definitely, I would say, the beginning of co-packaged optics. Obviously, there are many people, many companies, as well as research groups that are working on co-packaged optics, and I alluded to some of the key challenges, right? What are really the big challenges, specifically, in this domain of co-packaged optics? Putting it into the system, into the real ecosystem of manufacturing and industry. And there's 2 big things, right? One is the laser, We need to have a source of photons, right? So how is that laser packaged, within the system? There are definitely some really good approaches. And it also has to be the right laser that can generate, the number of wavelengths, all the things that we need. and the energy consumption. And then the second big part is how do you put that photonic chip into the package, into the ecosystem with the optical I/O, right? The silicon photonic chip is fine, no problem. We can put it on the wafer, we can assemble it. There's many techniques for everything from wafer bonding to assembly, that's all good. But how do you get that optical I/O, right? It has to connect to a fiber. I started to talk about some of the challenges there. Those are the key challenges for really getting co-packaged optics into our future. So is 2024 the year? I think it's the beginning. And I will also add optimistically that we will not be able to get to where we want to be with these systems, especially the AI systems that are dominating the world, without co-packaged optics. So we need it. We need to get there. Yeah.
Thank you very much. Just to tell you, if you put a question into a WOBA app, you can also vote for other questions. So you can push them up, and we will look on who got the most votes to select. Little game, so you may check and then agree on the questions if you like. And you put your own question. The next, which is maybe risen up now with the most likes, would be the next one. Would you agree that we choose this together?
Yes, that sounds good.
Okay, then.
Also, there's a live question later.
Yeah, let me see, I didn't see that. Yeah. So maybe we mix. Then first the live question and then the next from the WOBA. Please, sir, please introduce yourself and pose your question.
Ravi Mahajan, Intel. Keren, that's an excellent talk. Yesterday, when the idea of co-packaged photonics was discussed with system architects, they pointed out that the energy price of conversion in SerDes is the real killer in energy. Do you have any thoughts on how we can make wide and slow viable so that we get rid of the SerDes conversion completely? And then how do we standardize the wide and slow?
Yeah, absolutely. In fact, that was exactly our approach that I'm a big champion of, right? So I come from a background of sort of at the intersection. I'm always at the intersection of computing and photonics. And I really like to look at things from the system side. And in the past, folks in the optical world, they work on very, very fast modulators, for example. 100 gigabit modulators. Wonderful. You can get a nice, research paper, and it might be very useful for like long-haul telecom applications, but it doesn't work in the computing because, that interface. If you look at the electronic side of the interface, we have many, many parallel, as we all know very well, right? So what is that impedance matching from the optical side? And it's in the wavelength domain. And we have another domain for the future that we're working on, I just want to mention, which is the modal domain. You can also get orthogonal spatial modes of optics on top of the wavelengths. So there's even room for scaling. But let's stick with the wavelengths. And so I think the key here is, the dense wavelength domain. And then what you can do is you can dial down the data rate per channel. That's where we're going. And if you dial down the data rate per channel, you can find an optimum where, as we've shown, where the energy consumption is really minimized. And you don't need to have the SerDes. It's a SerDes-less, essentially, transceiver. Very different than some of the mindset and some of where the telecom folks are, right? And if you go to one of our conferences like OFC, there's almost like two different communities that are trying to get together. There's the telecom community there. I want to go fast. I want to have, lithium niobate, thin film modulators. But that technology will never solve the AI problem. It will never solve the AI problem. To get inside the AI socket, you need to have wide, slow, relatively slow, SerDes-less transmission, and necessarily requires dense WDM, which leads us to the comb laser technology. That's why I mentioned it's so critical to that.
So a follow-up then, is the dense laser comb technology ready for prime time, or do you think it has still some time before it becomes mature?
Yes, I believe that Obviously, you know, I have some bias because I have a company, Escape Photonics, that's developing that. We feel that, you know, we started the companies because we feel so strongly that this is the direction that we need to move in. And so that's one technology. There are other companies out there that are also developing this technology. And it's absolutely necessary. Now, in terms of, you know, I'm not a marketer, but, you know, what I know about the market is that currently the point where at least you know, customers and so forth, companies want the comb is around the 16-channel mark. And very soon, I believe it's going to go to the 32-channel mark. And yes, those technologies are commercializable today, absolutely.
Thank you.
Yeah.
So thank you very much.
Yeah.
It's just a little organizational thing. So thank you very much for your question. Now let's give others a chance to ask further. And I think we have a rising champion here in the questions. Now got 13 votes.
Oh, wow.
Should we take this now?
Sounds good.
Oh, good. Then I read it. So thank you very much. Can you please highlight the key technical barriers that this community can help solve? Yeah? Where should the focus to drive successful adoption of co-packaged photonics should go for or should be? Yeah?
Yeah, excellent question, and thank you for asking that. I think that, you know, this is a very difficult. It's a difficult challenge, right? There's a bit of a you know, chicken and egg, if you will, because some of the large, you know, packaging companies out there want to get into the photonics, you know, to the co-packaged photonics business, but at the same time, that business is not quite there, right? It's still as I showed, you know, there's still this active alignment. There's a lot of different standards, and you know, you can't like say, okay, turn on, you know, and here you go. There's a manufacturing of a photonic chiplet, you know, photonic IH, and we're not quite there yet. And so and in addition to all of that, you know, this is not a problem that's going to be solved by the photonics community, and it's not a problem that's going to be solved by the electronics community, and it's not a problem that's going to be solved by the packaging, you know, community. It has to be solved by really all of those multidisciplinary communities working really closely together. So there's a challenge out there about getting this ecosystem to fruition. And so I think that what we need to do as a community is really start to do some of these real prototyping, real pilot lines, you know, prototyping, where there's tremendous available tools and technologies on the back end, on the packaging that are out there. I know because, you know, we've had access to some of them, fortunately. But they're not, you know, they're working at the wafer scale, and they're not quite developed to, you know, so that they accommodate some of what's needed from packaging, co-packaging the photonic chips as well. So as an example, you know, a very exciting, you know, fiber I/O package, right, is to actually bring the fiber from the top into what we call an evanescent coupling into the chip. And that, it can have very low losses, can be done at high densities and so forth. But what we need to do that is we need to have access, you know, etch access to the optical waveguide. Just a kind of a small detailed example. So we need the fabrication of the photonic wafer to work, you know, to work into this ecosystem in a way that can open up that photonic waveguide and can develop the packaging technology for that. So it's, unfortunately, I don't have an easy answer for that other than to say that, you know, we really need to have concentrated effort, you know, to start to build some of these prototype packages so that they become a standard and can develop into a real manufacturing ecosystem.
Yeah, thank you very much. I should mention this question has been asked by Ravi Mahayan and the first by Michael Liu. Now let's look. Is there any additional question in
There's
the
a fellow
microphone?
at
There's
the
a second
speaker, yeah.
Yeah, please. So now we take an oral question from the auditorium here over the microphone, please. Please introduce yourself and then.
Thank you, Krishna Chetri from Corvo. So, adding chiplets with different functionality on the 3D stacking sounds very fascinating. And you mentioned some of the challenges there, but in general, I see one additional challenge is the doing so, we are running out of the real estate margin, right? We already have a very high density of vias which are connecting from one layer to the another layer. So do you still think that this approach could be scalable? And my follow-up question is, do you have a timeline in your mind where this technique can be more ready and mature to be commercialized? Thank you.
Yeah, so the first part is on the real estate, right? That's the footprint that's available in the 3D package, if I'm correct. And yeah, this is certainly, this is an important problem and challenge. The way that I would, at least the way I'm thinking about it, is in more of a chiplet ecosystem, right? And I think that if we can bring the photonic I/O, right, as a separate chiplet initially, right? It's a separate chiplet, provides very, very high bandwidth density to take that bandwidth outside of that package. So it's not necessarily the technology that's going to be used, within, the other 3D stack that you have there with the memory, the GPUs, and all of that, but it's just being used, for taking the data out of that package. So I think that, that's at least what I think is maybe the initial, very promising approach that still does not infringe on, some of the real estate, some of the other aerial important, that you need to have some of the other components occupy. And so that's where I see the first. That's why I keep saying it's going to be photonics to the socket, right, to that package, not necessarily all the way inside the 3D stack. Maybe in the future there'll be other approaches that bring it even within the 3D stack. Honestly, I don't think photonics necessarily wins there, because the electronic density and the electronic energy consumption is actually quite good. So that's the first part. The second part on the maturity of the ecosystem, optimistically, if you look almost at every major company, of course, global is a very important component of that ecosystem. There's a lot of investment and a lot of effort that's being put into photonics in general. And some companies already have very large programs, others are just getting into it. And so I think that the maturity of the ecosystem with all this investment that's going in will evolve. I see, that curve starting to bend in about 2027. That's sort of at least from everything that I've seen, all the different aspects, sort of in the 2-3 year time frame. I think that's really when we're going to see, larger scale commercializing and shipments, product shipments with the co-packaged photonics.
Thank you.
Yeah.
Thank you very much. Now we could maybe have a look to the WOBA app again. There's one actually going up with 12 volts. The others are already marked as answered. Should we take this?
Yes.
How can advancements in thermal management techniques mitigate the impact of heat on the optical performance of silicon photonics devices, and what are the current limitations? The question has been asked by Ravi Parthasarathi. Thank you.
Yeah, thanks. Very, very good question. Thank you for asking that one. So let me start by saying that photonics, no matter what it is thermally sensitive, right? You change the temperature, the index of refraction of the photonic material will change for the most part, and that will affect the performance of the photonic chip. Now, it can be more sensitive or less sensitive, and that's a lot of what we work with. So when you have, as I've shown you, some of the resonator technology that we have, in general, is very sensitive to temperature because it's a resonator, so you change the index a little bit, and there's a resonator effect, and that can change the wavelength and so forth. What we do to combat that is we can actually design the devices themselves to be robust to temperature variations to some extent. We can also design them to be more and more athermal. So for example, by combining materials that are changed in one direction with temperature versus another direction with temperatures. And that's all kind of areas where this community can be tremendously, can contribute tremendously to all of those efforts. So that's, in general, what's happening at the physical layer in the photonics. There's also device geometries that can be done to make them, again, more robust, less thermal. In addition to all of that, we have active control of the link. That's something that is actually already done. It's relatively simple circuitry that's used to control and maintain the link. And we've shown that even in our research groups, we can maintain the link over as much as 80 degrees change in temperature. But nonetheless, I think that paying attention to the thermal environment is a really key area, a really key challenging area that needs to continue to be advanced, and of course with cooling technologies. I'll just make one last comment, which is, we designed the photonic chiplet to be very low energy, right, by design. So for example, in that transceiver that I showed you, that's 120 femtojoules for the entire thing, right? The entire thing is turned on, constantly running data, and it's 120 femtojoules per bit. That chip is not hot. That chip is running quite cool, and we can keep it operating over long periods of time without any issues. The problem is going to be when we bring those hot GPUs nearby and other components within the package, and that's going to be part of all the thermal management that we're already doing in the packaging environment. Yeah.
Thank you very much. Then I think there is a next person there to question at the microphone. Please introduce yourself and pose your question.
Thank you for your presentation. Masi Barani, University of British Columbia. So the way I look at this is the enabler technology is the low V pi of this modulator, which is less than 1 volt. And what enabled that is the vertical junction that you used. So it's very good, greatly done, but doesn't that limit us to a certain foundries that provide that vertical junction? The rest of the industry, typical silicon photonics, they're lateral. And so can you please comment on that? Maybe technologies like these would push the silicon photonic foundries to go all vertical. So.
Yeah, so on the bandwidth of the vertical junction modulators, we've been able to, it's really more of the contact design, the RF contact design. So we've been able to run it easily up to 32 gig in the vertical junction. We can probably push it, we have some next generation designs, can probably go to 64, pretty readily. You're correct that some of the lateral junction designs can go obviously been shown to go even faster. But I would contend that, we don't necessarily, so there's a design space for sure. There's always going to be, pluses and minuses. Do we want to go to a 100 gigabit modulator? And because on the back end of that, you have to have not just the driver circuitry, but you have to have the receiver circuitry with enough sensitivity, and that's where you get a lot of the power consumption. So, this is that design space. We want to, we need to really push down the total energy of the link, including the laser, to under, way under a picojoule, hopefully under half a picojoule and even less. And it's really hard to see how you get there with, 100 gigabit modulators, even if whatever technology you use to make them. Mm-hmm. Yeah.
Thank you.
Yeah.
Yeah, thank you also from my side. Then the WOBA app now presents us again a champion with 10 votes. Would you like to have the question answered?
On reliability?
Yeah,
Sure.
so
yeah.
it's short and it means, can you comment on reliability, please?
Absolutely. So let me start by saying this is not my area of expertise. I'm not a reliability expert. It's not something that you know, we do a lot of in the academic world. But you know, of course, in the industry world, this is really, really important. So the photonic, you know, the photonic chip itself, right, the silicon photonic chip, the reliability is, you know, there's certainly companies that have been shipping silicon photonic transceivers, you know, and the reliability has certainly been addressed there, and it's you know, similar to basically, you know, other silicon chips. The issue with photonics is going to be on the laser. You know, that's where you know, some of the reliability questions, you know, come up, and we have lasers that have been qualified for telecom applications, and of course, you know, with lots of reliability data there for, you know, long-term operation. And if the new laser technology, as it's being developed for the datacom application, you know, within the AI systems, that needs to be addressed. Now, as I mentioned, there are different approaches. For example, the comb laser technology. The comb laser that I mentioned that we're developing, this very broadband comb with lots and lots of wavelengths, it's actually being driven, right? The comb is driven by a telecom laser. So kind of the reliability of that system is already baked in. It's already proven to be reliable because it's a highly reliable telecom laser source. You know, other approaches have, you know, lasers that, for example, are you know, quantum dot lasers that are grown on top of the silicon wafer. The reliability of those still needs to be shown and proven and worked out for longer term. And again, so it depends on the specific technology and the specific approach that's being used, where, you know, where we are in the reliability roadmap for the different photonic technologies.
Thank you very much. This question has been asked by Igor Arsovsky. And I think now we are coming to an end of our session and to the end of the Q&A. I would like to thank you cordially again for this really fantastic performance, and thank you for being here to bridge to our community. Please join me, and you have not to hesitate. You can be loud to thank her and to connect her to our community. Thank you very much, Keren.
Thank you, Karl.